TSP can be cast as a sequence optimization problem. We have different decoding techniques, and finding exactly the optimal sequence of the nodes by exhaustive search is intractable, given the O of n factorial complexity. Therefore, approximations are necessary, and the simplest approximate search is the greedy search, where at each step, the next node is the highest probability is selected, and its complexity is a linear of O of n. Better sampling techniques such as beam search or Monte Carlo tree search are known to improve results over this greedy search in TSP. Their complexity is O of Bn. Here, B is the number of beams in case of beam search, or the explored paths in case of Monte Carlo tree search. Beam search is a heuristic search algorithm that examines a graph by extending the most promising node in a limited set. Beam search constructs its search tree using breadth first search. Monte Carlo tree search is a probabilistic and heuristic driven search algorithm. It focuses on the analysis of the most promising nodes, expanding the search tree based on random sampling of the set. The final set of nodes of each tier is then used to weigh the nodes on the tree so that the better nodes are more likely to be chosen in the future. Now, moving to analyze the numerical experiments from the paper. The results are divided into two columns. TSP 50 is where we consider 50 cities or nodes, and TSP 100 is for 100 nodes. The OBJ objective shows the total length of the path or tour. So lower the objective, the better the result. Gap is the difference between the solution that we get and the optimal solution. In this case, we have considered the optimal solution to be Concord. Hence, the gap for Concord is 0.00%. T time means the total time for 10K TSPs in parallel, and I time means the inference time to run a single TSP in serial. So first, we can see that Concob and Gurobi are the integer programming algorithms. These are followed by the heuristic algorithms. The best heuristic algorithm is LKH3. Then we have the neural networks with greedy sampling, where we take the max probability in each decoding step. After which we have neural networks with advanced sampling by using beam search or Monte Carlo tree search. Here we can see that for TSP 50, using greedy sampling, we get a gap of 0.31%. And by using beam search, it drops the solution and it becomes very close to optimal. For TSP 100, using greedy sampling, we get a gap of 1.4%. And using beam search, it again drops, this time to 0.39%. To get an idea of the path obtained by this model, we compare the path obtained by the model versus the Concord. For first starting with TSP 50, we can observe that sometimes the neural network is even able to do slightly better than Concord. As in the first example, where the length using neural network is 5.576, while that with Concord is 5.585. Other times it is not better, but it is doing pretty well. Now comparing TSP 100, we can see that it does not do as well as Concord, but it is doing pretty well. The path for the first example, for example, is 7.89 versus 7.77, which is pretty close. Next, comparing the complexity. The complexity is exponential for Concord and polynomial for neural networks. We see the blue line denoting the performance of neural networks versus the Concord solver. The difference is quite evident as we keep increasing the number of nodes as the graphs deviate. Some of the conclusions that we can now derive from this presentation are similar to the advances in NLP and computer vision, deep learning and transformer architecture can also be used to solve combinatorial problems. The proposed model improves learned heuristics for TSP 50 with a gap of 0.004% and for TSP 100 with a gap of 0.39%. The results can be further improved by using better sampling techniques such as beam search and Monte Carlo tree search. It is important to keep in mind, though, that neural network solvers often offer faster inference time, which is of 0, O of n square L versus O of n power 2.5 B of n. But traditional solvers like Concord and LKH3 outperform learning solvers in terms of optimality and generalization. We can use learning techniques as a leverage to improve traditional solvers like leveraging branch and bound technique. Selecting the variable to branch is critical for search efficiency and relies on human-engineered heuristics such as strong branching, which is a high-quality but expensive branching rule. Recent works have shown that neural networks can be successfully used to imitate expert heuristics and speed up the branch and bound computational time. Future work may focus on going beyond imitation of human-based heuristics and learning novel heuristics for faster branch and bound techniques. This topic of research will naturally expand in the coming years as combinatorial problems such as assignment, routing, planning, scheduling are used every day by companies. Finally, thanks to Xavier Besson and Thomas Lawler, the authors of the paper Transformer Network for Traveling Salesman Problem, which we have followed throughout this presentation. Thank you.